We are continuing our lecture here. This is 14B. And so we are going to be continuing our conversation of chapter 14. There's a lot here, which is why I broke it up into 2 lectures instead of 1. But you will get to play with these concepts over the next couple of days with some labs. So hopefully the comprehension begins to sink in. Yesterday we talked about what controls rates of reaction and how fast reactions go. Now we're going to talk about how to calculate the rate with regard to concentrations of products and temperature and things of that nature. So yesterday was more conceptual. This one is going to be more applied, but we're still talking about the speed that reactions progress and how we can manipulate that. All right. So reaction mechanisms. A balanced equation may not show all of the steps of a chemical reaction. They tend to say, here we're going to mix these 2 things together, and we're going to get these couple of things afterwards. So we give you the reactants and the products, but not necessarily all of the intermediary steps. Because when the reaction actually happens, you have all of these activated complexes of this ran into this in the right orientation so that it's stuck together. But then after it's stuck together, there may be several steps that happen before we wind up with the products that we write down at the end of the equation. So substances made and then destroyed, which we call intermediates, don't show up in a chemical reaction. We don't tend to write these 2 things yield this, which yields this, which yields this, which yields the products. We tend to just write reactants and products, and we omit all of the intermediaries. But those intermediaries exist. They are created and destroyed, and the process flows through to the end. So when we talk about a reaction mechanism and what happens, we need to know that there are these intermediary steps, because all of those intermediary steps represent action potentials, and they represent activation energies, and there will be energy transfers between all of those steps. So we need to look at all the things that are made and all the things that are destroyed. And so the same atoms or electrons may bond in several ways before their final arrangement. So the animation that I showed you yesterday of a reaction with a little molecule running into the back of another molecule and sticking, and then part of the first molecule flying off. That little animation is an example of an intermediary, because for just a split second there was the one molecule and the other molecule that had run into each other and stuck. And for a moment that existed before part of the first molecule went flying off. And so that would be an intermediary. But oftentimes it's much more complicated than that. Oftentimes it's like it sticks and then it has to spin and stick again, and then something else breaks free, and there's lots of geometry changes. It looks kind of like a Rubik's Cube, where molecules will stick and flip and stick again, and part of this will break off, and we have all of these steps that it has to go through before we wind up with the product. Okay, so we want to start to kind of blow up our concept of a reaction being just a simple mix together and proof. There it is. It looks like that, but in truth, it's much, much, much more complicated. I don't know why this GIF is not playing. I'm all, well, darn. You were supposed to get, what the heck? I'm a bit scared. Yes, because of all the things that are happening here. But it's okay. It's okay. It's okay. You'll make it. Okay. So, when we look at all the different steps that happen in a chemical reaction, we have to find the one step that controls how fast a reaction occurs. Some steps happen instantaneously because of the way the Gibbs free energy thing is balanced, because of the way that the entropy and the enthalpy influence it together. Some steps are instantaneous, and some steps take time. And so we need to look at all the steps in a chemical reaction, and we need to kind of find the sticking point. What part of the reaction slows the rest of it down? There's a common phrase that a chain is only as strong as its weakest link, right? But and a chemical reaction is only as fast as the limiting step. What part of the chemical reaction is the slowest step? And then if the rest of the reaction, could go faster, it can't, because it can't go any faster than that one rate limiting step. So the rate limiting step controls the speed of the whole reaction. If step A, B, and C can be instantaneous, but step D takes a long time, and then E, F, and G are pretty fast too, it's that one step that slows the whole thing down. Imagine if each step in a chemical reaction were to be represented by a runner in a relay. And if the person leading off the relay is fast, and the anchor person of the relay is fast, but the middle guy of the relay is not all that fast, then the team is going to be limited by the slow guy in the relay, right? And so the same thing occurs if we have a chemical reaction and there are several steps. The speed of the whole reaction is going to be determined by the slowest step. So that's the rate limiting step. Okay, we have to find what that is. Usually that's found experimentally. Okay, the concentrations of the reactants of this step control how fast the whole process happens. So if we were to take a chemical reaction and blow it up and show every intermediary step, and then we determine which one is the rate limiting step, we now want to zoom in on that one step of the chemical reaction and analyze it. And we could write a statement that says, the more we increase the reaction ingredients, the reactants of that step, the faster that step will happen. And then if that step happens faster, the whole equation happens faster. Okay? Concentrations of the reactants of that step control how fast the whole process happens. Okay? So we write things called a rate law. I'm actually going to pause and let you write all this down because I want you to focus on this next step. Okay, so the rate law is a mathematical expression, and we will say that it is a constant, and we just say K, and we can experimentally determine what K is. It's a constant multiplied by the concentration of the reactants in the limiting step. So if this is the limiting step, we determined that water is in abundance, right? It's readily available. It's in excess. Then we would say that the more of this compound you have, the more speed the reaction will experience, because we're putting more of these things together in one room. And remember, or in one beaker, remember the analogy yesterday. The more Abrahams and Renees there were, the more likely that they would run into each other and have a reaction, right? So the concentration of this determines how fast this whole reaction happens. And we would say that the concentration of this substance times some mathematical constant will give you the number of moles per second that this chemical reaction happens. Okay? So we would bracket this and we say the concentration of C4H9Br times K gives you the rate. As the concentration of this goes up, then this whole reaction speeds up. So this would tell you that the concentration of the product doesn't matter, doesn't control the speed. The concentration of water does not control the speed. The concentration of hydronium does not control the speed. It's only the concentration of this that controls the speed. And so we've identified that this is the rate limiting reactant. And so that expression is called a rate law. It has identified what's the slow thing. And as we boost this up, the reaction will happen faster. So notice that the concentration of water doesn't matter in this reaction. It's not rate limiting. So we could have as much water or as little water, and we might not get as much product if we don't have enough water, but it doesn't make it go faster. So we've identified the rate limiting step. We've said it's not the amount of water that does it, it's the amount of this substance that does it. Okay? And for right now, the concentration of products don't matter for this example. So the value of K is always experimentally determined, and it's different for every reaction. So this is something that you will do labs and discover how to calculate K. That's what we're going to start doing tomorrow, and we're going to do that throughout the week. Okay? This whole thing is called a rate law. So that's the name of that mathematical statement. The rate equals K times the concentration of C4H9. Okay. Okay, so in that last example, we said that only the concentration of that one reactant influenced the speed of the chemical reaction. You could write rate laws for the rest of the things in that reaction, but we would want the math to show that these other things didn't matter. And so one way to reduce a number to 1 so that its multiplication doesn't matter is to raise that number to the 0 power, right? Any number raised to the 0 power is 1. And so when you put that in a mathematical expression and everything's being multiplied by 1 doesn't matter. So one way to say that the concentration of this thing is hollow, is meaningless, is to bracket that and say concentration of this and then raise it to the 0 power. And that makes the math say, yeah, it doesn't matter. We call that a zero order reaction. So we don't say exponent. I don't know why they don't say exponent. It is an exponent, but brilliant chemists hundreds of years ago said, oh no, we're going to call that an order. Whatever. It's an exponent, okay? So the exponent that we raise the concentration to is called an order. So that is a zero order reaction for water. If we don't put an exponent there, then obviously, just like in math, what would be the assumed exponent? 1, right? Raised to the first order, raised to the first exponent. So we're saying that this concentration, this part is first order. Okay, it's assumed 1. This is 0 order. It doesn't matter. Before I advance the slide, use your brilliant minds. And in this next example here, where the concentration of nitrous oxide is raised to the second and bromine is 1, what would we call this? If this is 0 order and this would be first order, this would be second order. Wow, he's smart, right? Okay, yeah. So whatever the exponent is, it's that order, okay? They just call it an order, it is an exponent. And so if this, in this example, what they're telling you is that the concentration of nitrous oxide influences the rate much more than the concentration of bromine. But bromine does influence it. But this would influence it to the first order. So as this goes up linearly, the rate would go up linearly, right? It would be a direct relationship. You double the concentration of bromine, the reaction would go twice as fast. But if the concentration is raised to the second power, then what they're saying is if you double the concentration of nitrous oxide, the rate does not increase 2, the rate would actually increase 4-fold. So this is an exponential increase in rate. As the concentration of nitrous oxide goes up by a factor of 2, the rate would go up by a factor of 4. If the concentration of nitrous oxide went up by a factor of 10, then the rate would go up by a factor of 100, right? Because it's an exponential increase in rate. So this would be called a second order. Oh, we already said any concentration without an exponent is assumed to be first order, right? It's all assumed to be 1. And the reaction goes up as, if the reaction goes up as a square of the concentration of nitrous oxide, then you can call it a second order. And then again, you could logically determine here in this third example, the reaction rate goes up as a cube of the concentration of methane or methane. It's just kidding. What is that? Ethene. There you go. But this would be a third order. And so if we doubled the concentration here, if this were to go up by a factor of 2, then the rate of the chemical reaction would actually go up by a factor of 8, right? 2 to the third power. If this were to go up by a factor of 10, we increase the concentration to by a factor of 10, then the rate of the reaction goes up by a factor of 1,000. So when you find something like this, you're saying, oh my goodness, if I double this concentration, the reaction goes up exponentially more fast. That's bad grammar. It goes exponentially faster. There you go. Then you have to figure out what is the exponent there. What is the rate law? Is it a first order, second order, third order? And all of this is determined experimentally. You can't do math and figure this out. You can't look it up in a table. You have to take a reaction and fiddle with the concentration of things and find out how it influences the rate of the reaction. And then you can write these things after you've done the experimentation. Okay, so this is a way of expressing that. Okay. In simple single-step reactions, the coefficients of a balanced equation predict the rate order. It's not always true, but it is a way of, it's a starting point. You can predict what it will probably be, and then you need to go do experimentation and verify. Okay? So if, for example, you were to be testing the synthesis reaction of nitrous oxide and bromine to make NOBr, you write the balanced equation, and you find out that to balance the equation, you need a coefficient of 2 in front of the nitrous oxide and not in front of the bromine, then a starting point for a rate law would say, hey, I bet that NO squared BR is the rate law. And you could start with like a hypothesis of that, and then go into the lab and test it and see if in fact that's true. That if you double the concentration of nitrous oxide, that the rate law actually goes up by a factor of 4. And if you triple the concentration of nitrous oxide, then 3 squared, the rate law should go up, the rate of the reaction should go up by a factor of 9. So you can determine that experimentally, and a good starting point is to write a hypothesis rate law with coefficients as exponents. So the 2 here becomes a 2 there, and the 1 here becomes a 1 here. It usually works that way. It doesn't always, but it usually works that way, and at least this is a place to begin. And then as you fiddle with rate laws, you can mess with the exponents until it works. But it's a good starting point. Okay. Now, in a multi-step reaction where there are a bunch of intermediaries, it doesn't help you. But in single-step reactions, then it's a good place to start. Okay, so let's do an example. One of the most amazing reactions to watch is thermite, the thermite reaction, where one oxidized metal is reduced by the oxidation of a more reactive metal, creating a lot of excess heat. And so one example of that would be iron oxide plus aluminum. And we get this thing hot enough to get started, and the iron loses his oxygen and the aluminum picks it up. So this is a single replacement reaction, right? This is the Flintstones go to a dance, and then Barney shows up, and Wilma winds up dancing with Barney, right? Okay, so this is a single replacement reaction, and as we watch how this happens, we need to determine what's the concentration here, what makes the reaction go faster or slower. In this reaction, it's been determined that the rate is independent of the concentration of iron oxide. No matter how much iron oxide you have, the speed will be the same. Now, obviously, it'll go longer and it'll go more if there's more stuff to do the reaction with. But as far as how fast it happens, the iron oxide does not influence the rate. So that would be a zero order. If we were to write FeO2 or Fe2O3 in brackets, we have to put 0 next to it to say it doesn't matter. Okay. Also, the rate went up by a factor of 8 when the concentration of aluminum was doubled. So experimentally, we determined that the aluminum, doubling the aluminum made the reaction go 8 times faster. So you've got to be good with squares and cubes and 4th powers and 5th powers, and if you're not good with it, you have a calculator. 2 raised to the what power is 8? What? 3. 2 raised to the 3rd power is 8. So if we doubled the concentration of aluminum, the reaction went 8 times faster. So you've got to figure out, okay, if I multiply this by 2, it's 2 to the something power is going to give me the rate. So 2 to the 3rd power is 8. So rate went up by a factor of 8 when the concentration of aluminum was doubled. Express the rate law. Iron oxide doesn't matter, so we can raise that to the 0 power. Right? That's a 0 order reaction. We don't need to write that part. Okay. Got it? Yeah. Okay, good. So, I know, I'm strange. It's okay. How do we express that the rate went up 8 times when the concentration of aluminum doubled? 2 to the what power is 8? 2 to the 3rd power is 8. And so the rate law is concentration of aluminum raised to the 3rd power. Okay. I'm strange, but that's okay. You love me anyway. This is that reaction. Just so you can see it. Hold on.